Hello, ma'am.
Yeah.
Ma'am, good afternoon po. Ma'am, some of our classmates po are in the waiting room po.
Okay. Thanks.
Okay po.
Thanks, VJ. Okay. So first is get the mean. What is the mean of C sub n? Okay. So note that so just use the formula for the mean. So the formula for the mean is the expected value of a random variable x is the sum of x times the probability of x. Note that we have a discrete distribution. Okay. So z sub n can take on either the value c or n. Okay. C with probability 1 minus 1 minus n with probability 1 over n. Okay. So C with this probability and with this probability. Okay. So this expression reduces to C minus C n minus 1 plus 1. Okay. What is the limit of the expected value of C sub n approaches infinity? So this is the okay, so this is the asymptotic mean. Okay, so we get the limit of this. So the asymptotic mean is the limit of C minus C n minus 1 plus 1. Okay, so n appears only in this term. So as n approaches infinity, C over n would approach 0. So we have C plus 1. Okay. So note that though the PLM of C sub n is equal to C, the asymptotic mean of C sub n is C plus 1. Okay. So as n approaches infinity, the mean would be C plus 1. So beyond a certain n, the mean would be C plus 1. Okay. So our question now is, does the C sub n converge in mean squared to C? That is this notation. Okay. So we use this definition of convergence in mean square. So we have the limit of the expected, well, we first solve for the expected value of C sub n minus C square. Okay. Note that you're getting the expected value of this function. So note that the expected value of a function of x is the sum of g of x times the probability of x. Okay. So using this, okay, so we have C sub n. C sub n can take on the value C or n. Okay. And these are the corresponding probabilities. Okay. Okay, so the first term would be 0. And then for the second term, we have n minus c squared n to the minus 1. Okay, so we're left with this expression. Okay, then we get the limit of this as n approaches infinity. Therefore, we get the limit of this. Okay. So note that here you apply L'Hopital's rule, because if you substitute infinity, you would have infinity over infinity. Okay, so you have the limit of the first derivative of this with respect to n is 2n minus c. This with respect to n is 1. Okay, but as n approaches infinity, the limit would be infinity. Okay, therefore, the limit of this expression is infinity. Okay, which is not 0. Okay, therefore, c sub n does not converge in mean square to c. Okay. Okay. Therefore, for this random variable, we have the filim of c sub n is equal to c, but then, so that is c sub n converges in probability to c. But then c sub n does not converge in mean square to c. Okay. So note that the convergence concepts are not equivalent. Convergence in probability does not imply convergence in mean square. Okay. So from this example, we can infer convergence in probability does not imply convergence in mean square. Okay. Now let's go to convergence in distribution. Okay. So the notation for convergence in distribution is this. And
Ma'am?
yeah,
Excuse me po, ma'am. May naiwan po ma'am sa waiting room po, si Angela po.
okay.
Thank you po.
She must have left. Wala. She must have left. I think she must have left.
Sige po, ma'am. We're trying to contact her po, ma'am. If baka po ano lang po siya, nag-log in po ulit.
There she is.
Thank you po.
Yeah, she's back. Okay. So we have convergence in distribution if the distribution function of x sub n converges to the distribution function of x at every continuity point of f. Okay. So this definition holds for discrete and continuous random variables. And note that it is not the sequence of random variables that that will be converging, but it is the sequence of CDFs, okay, converging to some CDF, okay. So you're looking at F sub n, X sub n, and you are looking at whether this converges to the CDF of X, okay? So F is the CDF. So we say F is the limit distribution of X sub n. And convergence is in distribution is the weakest form of convergence. Okay, and we will see later why we say it's the weakest form of convergence. Okay, let's have an example. Okay. Let Z have let the random variable Z have a Bernoulli distribution with P is equal to 1/2. That is, C can take on the value 0 or 1, 0 with probability 1/2, 1 with probability 1/2. Okay. Then define C sub n is equal to 1 minus C for all n greater than 0. Okay. So let us look at C sub n. C sub n, the C sub n is 1 minus C. So this would be 1 with probability 1/2, 0 with probability 1/2 also. So this is with when C is equal to 0 with probability 1/2, C is equal to 1 with probability 1/2. Okay. But note that C sub n and Z have the same distribution. Okay. They're both Bernoulli. They're both Bernoulli with P is equal to 1/2. Okay. Okay. As an exercise, suppose Z is Bernoulli with probability 1/4. Okay. And you define C sub n is equal to 1 minus C. Okay. The question is, does C sub n converge in distribution to Z? Okay. So I change this probability and see if you still have convergence in distribution. Okay. So we know this C sub n as defined here converges in distribution to C. Now, let us see whether it converges in probability to Z. Okay, so we want to check whether the p-lim of C sub n is equal to Z as n approaches infinity. Okay. So we have convergence in probability. So we have to use this definition. Okay. So now we look at the distance between C sub n and C. Okay. So we have the distance between C sub n minus C, or that is the absolute value, is equal to the absolute value of what is C sub n. It is 1 minus C. Then we have minus C. So this is 1 minus 2 Z. But Z can be either 0 or 1. C sub n minus Z. So this is 1 minus 2Z. But Z can be 0 or 1. It is Bernoulli with probability 1/2. So if Z is equal to 1, if Z is equal to 1, 1 minus 2Z is equal to minus 1, right? If Z is equal to 0, then 1 minus 2Z is equal to 1, okay? But we're having the absolute value, so this is equal to 1, okay? So we get the limit of the probability that this absolute value is greater than epsilon as n approaches infinity. Okay? But the absolute value of C sub n minus C is 1. So the limit of 1 greater than epsilon as n approaches infinity is equal to 0 for any epsilon greater than 0 cannot be satisfied, right? Okay. This event is 1 greater than epsilon, or epsilon is greater than 1. Okay. But we have the condition for convergence in probability. It has to be any epsilon greater than 0. So epsilon here can be less than 1. Epsilon can also be greater than 1. Okay. Okay. So that means that C sub n does not converge in probability to Z. That is, the p-lim of C sub n is not equal to C. Okay. So note that convergence in distribution does not imply convergence in probability. But we have the previous result to that convergence in probability does not imply convergence in mean square. We also know that this does not imply convergence in mean square. Okay, from our previous example. Let's have another example. Suppose y sub n is normally distributed standard normal, mean 0, variance 1, y sub 0 is also normally distributed with mean 0, variance 1. So both random variables are have the standard normal distribution. Furthermore, let's assume that y sub n and y sub 0 are independent, okay, for all possible values of n. Okay. So trivially, we can see that y sub n converges in distribution to y sub 0. So the CDF of this converges to the CDF of y sub 0. The standard normal distribution converges to itself, right? They're just identical. Okay. Now let us look at y sub n minus y sub 0. Okay. So both are standard normal random variables. So the linear combination of normally distributed random variables would also be normal. But what is the mean? The mean is the expected value of y sub n minus y sub 0 is equal to the expected value of y sub n minus the expected value of y sub 0. But we get that from here. They're both 0. So the mean is 0. Okay. Now, what is the variance of y sub n minus y sub 0? So that is the variance of y sub n plus the variance of y sub 0 minus 2 times the covariance of y sub n, y sub 0. But then y sub n and y sub 0 are independent. So this is equal to 0. So you just have the sum of the variances. So this is 1 plus 1. So that is 2. Okay. So the variance is 2 for this difference. Now, look at the convergence, the condition for convergence in probability. It is this. Okay. Okay, so let's look at the probability of y sub n minus y sub 0 greater than epsilon. Okay. Okay. So this would be equal to some constant k greater than 0 for any epsilon greater than 0. Okay. So let us look at this. So this is y sub n minus y sub 0. And we know that this would be normally distributed. So this is the density function. So this is normal with mean 0 and variance 1. Variance 2. Okay. What is the probability that this is greater than epsilon? Okay. Okay, so if this is epsilon, okay. So we want the probability that the absolute value of y sub n minus y sub 0 is greater than epsilon. So the k here would be the sum of these areas. Okay. So k is the sum of the crosshatch areas. Okay. So it would be some constant k. Okay. Okay, that k would be the same for n is equal to 1, 2, and so on, since the y sub n's are identically distributed. Okay, so what is the limit of this probability? So the limit of this probability is equal to the limit of k, and that is equal to k, is constant, and it is not 0. Okay, so the concept, the definition for convergence in probability is not satisfied. Therefore, the p-lim of y sub n is not equal to y sub 0. Okay. Again, this is an illustration that convergence in distribution does not imply convergence in probability. Okay, so we have this theorem. Convergence in probability implies convergence in probability, which implies convergence in distribution. That's why we say convergence in distribution is the weakest form of convergence. So in notation, we have this. I think the proof is in Amemiya. You can have a look at that. Okay. So here in our previous examples for this and C sub n, we have seen that convergence in distribution does not imply convergence in probability. Okay, so we have 2 examples for that. And in our other example, we have shown convergence in probability does not imply convergence in mean square. So in our earlier example, we have shown convergence in probability does not imply convergence in mean square. Okay, this can be useful if you're asked to show convergence in probability. Sometimes it's easier to show convergence in mean square. So if you can show convergence in mean square, then it follows that you have convergence in probability. Okay. And if you have convergence in probability, that means you have convergence in distribution. Okay, we have other useful theorems here. Okay. Let x sub n be a vector of random variables with a fixed finite number of elements, and g a function continuous at the constant vector alpha. Okay. Suppose x sub n converges in probability to alpha, then the function of x sub n converges to the function of alpha. Okay. So x sub n is a vector of random variables. So suppose x sub n. Okay. You have a finite number of elements. Okay. So m is finite. Okay. And we have the PLM of x sub n, which is equal to, you just get the PLM of each of these. Let's say is let's say alpha 1, alpha 2, down to alpha n. Okay. So if you have a function g of xn1, xn2, down to xnn, then the PLM of this is equal to the PLM of g of alpha 1, alpha 2, down to alpha n. Okay. So note that here you are working with vectors. But here you are working with a function. So this is just one by one. This is just one by one. Okay. Okay. Actually, that makes operations of prelims easy to do. And an example of that is what we had earlier, I think, for the operations regarding prelims here. Okay, so let's take the second case. Okay, so the PLM of x sub n is equal to c, the PLM of y sub n is equal to b. So you have the vector x sub n, y sub n. So the PLM of this, okay, so that is the PLM of x sub n, the PLM of y sub n, and this is c, d. Okay, so suppose you have a function xn, yn, you want to get the PLM of that. So that is just c times d. Okay. So actually, these rules for the probability limit come from this result here. Okay. Now, we have this Slutsky result. Suppose x sub n converges in distribution to x and y sub n converges in probability to alpha. Okay. X sub n and y sub n are univariate random variables. Okay. Intuitively, we know that y sub n converges in probability to alpha, then that implies that y sub n converges in distribution to alpha, right? From this result. Okay. So note that the results here that follow is in terms of convergence in distribution, which is the weakest form of convergence. Okay. So x sub n plus y sub n converges in distribution to x plus alpha, the product here, and we have it here. Okay. So these results are similar to what we had earlier for the prelim, except that now we have a weaker convergence concept, convergence in distribution. Okay? Because one variable, one sequence converges in distribution to X only, while the other one converges in probability. So you pick up the weaker form of convergence. Okay. Then you have a similar result if you have convergence in distribution here. These are vectors. Then you have this, which are in terms of one by one. You have functions, so they are just scalars. Okay. Okay. Intuitively, this follows because convergence in distribution, because of this result. Convergence in probability implies convergence in distribution. Any questions there? Okay. Okay, so for these lecture notes, we just went over the concept of convergence in probability, convergence in mean square, and convergence in distribution. Okay, we'll move on to the limit theorems, where we will have the weak law of large numbers. There we would be working with prelims again. We have the central limit theorem. So here we'll be working with the normal distribution. Okay. Okay. So I'll be going to the weak law of large numbers. I have not uploaded it to the UVLE. I will do that later. Okay. Okay. So we'll go to the limit theorems. The limit theorems. We'll start with the weak law of large numbers. Okay. An important takeaway there is the sample mean converges in probability to the population mean. Okay. So if the sample size becomes sufficiently large, the sample mean would be a good estimator of the population mean. Okay. Suppose R is the number of heads in n tosses of a coin. Okay. And we want the probability of heads turning up in a toss. Let us assume that we have a fair coin and the tosses are independent. Okay. So if you have R over n, the number of heads in n tosses of a coin, R over n is the sample proportion. right? The proportion of the tosses that turn up heads. And from the weak law of large numbers, it turns out that the probability of this sample proportion converges in probability to the probability of heads in a toss of a coin. That is, when n is sufficiently large, the sample proportion approaches the true probability of heads in a toss of a coin. Okay. For the central limit theorem, I think we will take two versions. And one result there is that the binomial random variable, which is a discrete random variable, converges in distribution to the normal distribution, which is a continuous distribution. Okay. And we will have example of the normal approximation of the binomial distribution. Okay. Okay. So let's start with the weak law of large numbers. Okay, so let's have some lay out some notation here first. Okay, so we have a sequence of random variables, I going from 1 to down to n. Okay. Okay, so that is n is the number of times you pick out an observation from the population. Okay. So what is x bar sub n? So let us define that as the sum of x sub I going from 1 to n over n. Okay. So if you look at this is the what we call the sample mean, right? Sum of x sub I going from 1 to n divided by n. Okay. Now let us have this, let's form another random variable c sub n from x bar sub n. Okay, so let us have c sub n is x bar sub n minus its mean divided by the square root of the variance. Okay. Okay, then verify that this is true. Okay, that is correct. Expected value of c sub n is 0. The variance of c sub n is equal to 1. Okay, make sure you can get these results. Okay. Okay. There are different versions of the weak law of large numbers. We'll take probably the simplest version of the weak law of large numbers. Okay. So for the weak law of large numbers, we're looking at the conditions under which x bar sub n minus the expected value of x bar sub n approaches in probability 0. Okay. Okay. So this also implies that x bar sub n approaches in probability the expected value of x bar sub n. What is the expected value of x bar sub n? What is the expected value? So what is the expected value of what x bar sub n is the sum of x sub I going from 1 to n divided by n. So what is the expected value of this? What is the expected value of this? How do you get the expected value? Okay. Note that n is a constant, so you have 1 over n times the expected value of the sum of x sub I going from 1 to n. So that is 1 over n times the expected value of x sub 1 plus x sub 2 plus so on to x sub n. So that is 1 over n times the expected value of x sub 1 plus the expected value of x sub 2 plus so on to the expected value of x sub n. Okay. If they all come from the same population, let's say the expected value of x sub I is equal to mu I going from 1 to down to n. So mean does not depend on n, then that would just be 1 over n times n mu, or that would be mu. So this is equal to mu. Okay. So okay, so let us have this version. Khinchin's version of the weak law of large numbers. Let x sub I be independent and identically distributed with the expected value of x bar sub n is equal to mu. Okay. Then the sample mean converges in probability to mu, or the p-lim of the sample mean is mu. Okay. So note that the weak law of large number implies that the sample mean is a consistent estimator of the population mean. We will take, I don't know if you had properties of estimators in your boot camp, but what do you mean by a consistent estimator? So let's say theta hat is an estimator of the population parameter theta. If the p-lim of theta hat is equal to theta, then theta hat is a consistent estimator of theta. Okay. So here, this implies that x sub n bar, the sample mean, is a consistent estimator of mu. Okay. When we're talking of consistency, we're doing it in the context of large sample theory. So that is as the sample size, as n becomes sufficiently large. Okay. So to rephrase, let x sub 1, x sub 2, and so on be identically and independently distributed random variables. Since they are identically distributed, each of the x sub i's will get the same mean and the same variance. Okay. For independence, we need the independence assumption to get this sigma square. Okay. So define this x bar sub n, get the expected value of x bar sub n, variance of x bar sub n. So you can calculate this using this information. Okay. Then for every epsilon greater than 0, the probability limit of this expression is equal to 1. That is, x sub n converges in probability to mean. Okay, let us prove this Kinchin's weak law of large numbers. Okay, so to do that, we use Chebyshev's inequality. Okay, which says, suppose x is a random variable, g of x, a non-negative function. For any r greater than 0, then we have this inequality. Okay, we're working with probability limits, prelims, or convergence in probability. So let's look at this event. The absolute value of x bar sub n minus mu greater than equals to epsilon. Let's get the probability. Okay, so if we square both sides of this inequality, we get this expression. Okay. And using, so note that this is of this form. G of x greater than equal to r. Okay. So this is your g of x, and this is your r. Okay. So using this, then we have less than or equal to the expected value of g of x, which is x bar sub n minus mean square. R is epsilon square. Okay. But if you look at the numerator here, okay, mu is the mean of x bar n. So is the mean square deviations from the mean. That is just the variance of x bar n. Okay. But what is the variance of x bar n? It would be sigma square over n. So this is equal to mu, and this is sigma square over n. So if you get the complement of this event, okay, so the probability is 1 minus this probability. Okay. Then you reverse the inequality, and we have 1 minus this. Okay. And then if you get the limit of this probability as n approaches infinity, you have greater than equal to 1 minus the limit of sigma square and epsilon square as n approaches infinity. Okay, we have n here, so this limit would be 0, so you get 1. Okay. Okay, but if you look at this sequence, this says that the limit of the probability of x bar n minus mu less than epsilon as n approaches infinity is greater than or equal to 1. Okay. But probabilities cannot be greater than 1. So you need to have equality. Okay. But that is the condition for convergence in probability. Okay. So just go through the proof again. It's an exercise in the use of the Chebyshev inequality, getting the mean and variance. Any questions there? Okay, then we move on to the central limit theorem. Okay. So for the weak law of large numbers, this is our major takeaway. The PLM of x sub n is equal to mu. The PLM of x bar sub n is equal to mu. Or that is, the sample mean is a consistent estimator of the population mean. Okay. Now, when we move to the central limit theorems, we are looking at the approximate distribution of x bar sub n when n is large. Okay. So we're looking at the asymptotic distribution. Okay. From the weak law of large numbers, we have this. Since we're looking at the asymptotic distribution, let us look at the limit distribution of C sub n, which we defined earlier as this. Okay. Okay. And then we look at the conditions for which C sub n converges in distribution to the standard normal distribution. Okay. So here, we're looking at convergence in distribution. So the limit of f sub n, C sub n, as n approaches infinity, is the standard normal distribution. Okay, so note that this is the CDF, and this is just the density function for the standard normal distribution. Okay. So the first version is that of Lindeberg, Levi, which is probably one of the simplest form also of the central limit theorem. Okay. So let x sub I be independent, identically and independently distributed random variables. Note that this does not suppose any specific distribution of x sub i's. Okay. Our restrictions only is that expected value of x sub I is equal to mu, and the variance of x sub I is equal to sigma square. Okay. So these two conditions will not be difficult to fulfill if we are sampling from the same population. Okay. Okay, so here there is no restriction on the distribution. It can be exponential, it can be Bernoulli, it can be binomial, or whatever. Okay. The x sub i's need not be normal, but they should be coming from populations with the same mean and variance. Okay. So a sufficient condition for this would be if you are sampling from the same population. Okay. Then it follows that C sub n, as defined here, converges in distribution to the standard normal distribution. So note X sub I can be a random sample from any distribution, discrete or continuous. Here we require the sample size n to be sufficiently large because we're talking about convergence in distribution. This can depend on the skewness of the underlying distribution of X. If skewed, usually you require n to be greater than or equal to 30. If the underlying distribution is symmetric and less than 30, may give you good approximation using the central limit theorem. Okay, so those are just rules of thumb. So an application of Lindeberg-Levi central limit theorem is the normal approximation of the binomial distribution. Okay, so I think I did not give you. There are other versions of the central limit theorem, which I did not give you. So if you look at other books, there are other versions of the central limit theorem, and they just differ according to the assumptions. Okay. Okay. So the central limit theorems would differ depending on the assumptions, these assumptions. Okay. Okay, so let's go to a quick application of the Lindeberg-Levi central limit theorem. Okay, where we have the normal approximation of the binomial distribution. Okay, so let y sub I be a Bernoulli random variable. That is, y sub I can turn up 1 or 0, 1 with probability p, 0 with probability q, which is equal to 1 minus p. So note that the expected value of y sub I is p, the variance of y sub I is pp. Okay, this is easy to verify. Okay. Then we said earlier that a binomial random variable, say x sub n, can be expressed as the sum of Bernoulli random variables. Okay. Okay. And again, you can easily verify this mean and variance. Okay. So note that x bar n is defined as this. C sub n is the standardized random variable. We subtracted the mean and divide by the square root of the variance. Okay. So from the central limit theorem, x sub n divided by n, okay, x sub n divided by n minus p divided by square root of pq over n would converge in distribution to the standard normal distribution. Okay. So verify this, especially how you get this expression. Okay. Okay. X sub n is defined is this. Okay, then you can manipulate this. Then you would have x sub n over n would be normally distributed with mean p and variance pq over n. Okay. So from this line you go to this. Okay. So again, verify this. And then from this line, you go to this. Then you get this expression. Okay. So note that the parameters of the normal distribution change. Okay. So make sure you know how we go from one line to the next. Okay. I'll stop here. Work through this example. Okay. We'll quickly go through the two examples on Tuesday. Okay. Any questions? Okay. Okay, so that's it for today. So today is Thursday. I hope you had a good reading break. So start studying for the test a week from today. You do not have a class after 2:30 on Thursdays. So the exam might go from 2 hours to 3 hours. Okay. It's a closed book exam. So again, the coverage should be only up to special distributions, not the large sample field. Okay. And I will be providing you with the blue books and the scratch papers. I'll announce where the venue would be. It would be in the definitely, I think, in the library building, because the main building they're doing some construction work. You may use calculators, but no cell phone for the calculators. So you would not get in touch with each other. Any other questions? So you're all set. Okay. So just make sure you understand the concept. Again, it's closed book, so you might have to memorize some stuff. Okay. So enjoy the weekend, but study. Okay.
Thank you, ma'am.
Thank you po.
Okay.
Thank you
Take
po.
care, everyone.
Thank you po.
Take care po.